Okay, my friend. Let's look at a different thing today. Welcome back, and then last time we were talking about the calculus. This is again like kind of like applications of calculus. Applications of calculus heavily found in statistics. Let's look at this heavy problem that most of the students struggle with, this kind of problem in statistics and mathematics. Let's try to find a solution. Let's try to help them out. Look at this problem. Unlike in mathematics, we don't have variables in statistics. We have something called random variable, because that variable cannot be predicted ahead of the time. It has to be determined through just like a chance process or random process or probabilistic process. Because of that reason, this particular, as an example, that we're talking about the lifetime of a battery, lifetime of a computer, lifetime of electrical, electronic or mechanical components. Those lifetimes cannot be predicted ahead of the time. Because of that reason, it's going to vary from person to person. At the same time, it cannot be predicted ahead of the time. Because of that reason, we're going to call that one not like a regular variable, it's a random variable. In such a scenario, let's say that if you get into the more theoretical aspect, and later on we can talk about its practical application where that this can be heavily utilized. Let's say, look at this, let's read this problem. A random variable y, capital letters are heavily utilized in statistics to denote the random variable. Likewise, that we are using lowercase y to denote the function in mathematics. Y has a beta distribution. Beta distribution is one of the distributions that are available in statistical arena, and it's going to go from 0 to 1. Its domain is always 0 to 1, like it's kind of it can be even utilized in order to model CDF. CDF is also a probability. That probability can even be that model with this kind of a distribution, because the probability, as you know, that going to go from that 0 to 1 all the time. So the beta distribution, I can use this abbreviation for distribution. It's a second kind. In addition to first kind, the second kind, we have a first kind of beta distribution as well. If for these given parameters, which are called alpha and beta, these two both are shape parameters in this particular case. In statistics, there are three types of parameters: location parameter, scale parameter, and shape parameter. Those are the ones heavily responsible for the peakedness, lopsidedness, and elongation, and all kind of properties of any kind of a given distribution. So in this case, we are using this beta distribution of second kind, having two shape parameters alpha and beta, and with its density function, which is given by, in this format, f of y, capital Y, subscript y, y to the power of alpha minus 1 over beta function, see, beta function, alpha comma beta, 1 plus y to the power of alpha plus beta for this particular domain. Y is always positive. If that's the case, in such a case, this has been that in, let's say that this is kind of like a lifetime been modeled with this kind of a beta distribution of second kind. Now we are planning to model that it's kind of like a modification. Instead of going to y, they are interested in the practitioners, the experimenter, they are really interested in 1 over 1 plus y. Now we really want to find, which is denoted by u. U has been given by 1 over 1 plus y. Now we want to find its PDF. Let's see how to get this done, step by step. Okay. In order to get this done, what we're going to do, we're going to go back to this guy. See, u, we have 1 over 1 plus y. I'm going to rewrite same thing with the lowercase letters, which represent the realization of this random variable. Realization of the Realization means absurd values of the given random variable. Here, y as well as u are random variables. Given random variables u sorry, y and u are respectively given by simple y and simple u. So let's write the same thing, pretty much the same thing with the lowercase, 1 over 1 plus y. Then what we're going to do, we're going to get the y in terms of u. Okay, y in terms of u. See, y, 1 plus y is nothing but 1 over u. Then y is 1 over u minus 1. Then y is u 1 minus u. So we get the old variable in terms of the new variable. Then we're going to go ahead and find something called the Jacobian. Jacobian is nothing but, given by j, nothing but the derivative of this guy, old one, with respect to the new one. See? Old one with respect to the new one. So if you're going to go ahead and use this one, it's going to be far easier. That means I'm interested in taking the derivative of 1 over u minus 1 with respect to u. See? So let's take the derivative. 1 over u is nothing but minus 1 over u to the second minus 0, which is minus 1 over u squared. Therefore, I'm going to get the magnitude or absolute value or just the positive value of this derivative or the Jacobian. Value of the Jacobian, which is denoted by, that is j this one equals to nothing but, see, minus 1 over u squared, which is 1 over u squared. You see? Then we can easily write therefore the probability density, I can write probability like this abbreviation, density function. As I mentioned earlier, function will be written in this abbreviation, which is also abbreviated the whole thing by PDF of u is now f of u is nothing but f of y has been replaced with u times the Jacobian of absolute. See? Very easy. This is the new PDF. This is the old PDF. But in the old PDF, the domain or the independent variable will be replaced by this. Y has to be replaced by the inverse of u, inverse function. I'm going to write this one like h inverse u, h inverse u. See? Like that. Where I'm going to write here, where H inverse u is, you can remember, where H inverse u is nothing but y, which is 1 over u minus 1, or 1 minus u over u. That's what we had there, see. So pretty much what we will do, we get the PDF already given, which is for y, should be replaced by its inverse function, see. That means simply y should be replaced, rather than working with y, you jump into u. Now y has been given in terms of u in this format, 1 minus u over u, see. It's not a big deal, and times the absolute of Jacobian. So let's plug in over this one. Therefore, f of u is nothing but, we can remember our function 1 over beta, alpha comma beta. See, this is what I had earlier. I'm going to write this one first. 1 plus y to the power of alpha plus beta, and on the top I have y to the power of alpha minus 1, and we have y positive, see, y positive, see. So this should be replaced by, this whole thing should be replaced by y equals 1 minus u over u times absolute Jacobian, which is 1 over y squared, times 1 over u squared, you see. Therefore, f of u, this is u, this is a beta function. We can get back to the beta function and have a detailed discussion later on once we're done with this one. That's a different thing. Everybody who are in this class are very familiar with the beta function. Beta function can be expressed in terms of gamma function. Okay, those are special functions found in mathematics. So let's try to do this one first. So y is nothing but 1 minus u over u to the alpha, see, minus 1. I'm replacing this y, see, this y being replaced by 1 minus u, see, 1 minus u over u, and the parameter stays the same, over this function, these are constant, stays the same, plus 1 plus y, see. Easily, if you get the 1 to this side, you see, if you get the 1 to this side, 1 plus y is nothing but 1 over u, you see, 1 over u to the power of alpha plus beta times 1 over u squared, and y is nothing but, see, 1 over u minus 1 greater than this one. See? So I wrote that one outside that one, okay? Now you don't need this one. You don't need this one now. That's the domain. That's the domain. This is the domain. Domain. With the domain I wrote everything outside, pretty much everything, okay? See, this one is nothing but, see, f u, f capital U, simple U, that's the PDF of U. See, here what I did was I brought this one to this side, and then you bring this one to this side, negative become positive, this stays the 1 over U. Now let's simplify this one. That's all we got to do. Let's simplify. When you simplify this one, 1 minus u, see, I'm going to write very clearly, 1 minus u to the power of alpha minus 1. I'm going to write 1 over beta plus beta alpha comma beta here. Then you have a u alpha minus 1, this u squared plus 1 over u to the alpha plus beta. See, you can write like that. And here 1 over u greater than 1. You can bring the 1 to the other side. You see, I pretty much combine 1 minus u to the alpha minus 1, u to the alpha minus 1. See, this part taken care of first. You see, I kept this one in the denominator. In the major fractions, you have to keep this one in the numerator and then bring this one to the denominator. U to the alpha minus 1, I brought that one to the major denominator. 1 minus u in the major numerator. They split it, this stays the same. This I wrote the same way, see. And u squared, I brought this inside, see. Then let's simplify furthermore. See, then this is nothing but fu u. Then this equals 1 over beta alpha beta 1 minus u to the alpha minus 1 over this u. Let's say u, when you simplify, you have a u to the alpha here, you have a u to the minus 1 here, you have a u to the second here, you have a u to the alpha here, you have a u to the beta here, and you have 1 greater than u. I brought this u to this side and multiply. See? I just split this one. I didn't touch this one there because I don't see any other extra 1 minus u terms appear in this expression. So I don't want that to get cancelled with anything or then combine back again. Just leave as it is. I split this one, u to the alpha, u to the negative 1, u to the second, 1 over u to the alpha, u to the beta. So they get cancelled off. So you are pretty much left over with beta alpha beta times 1 minus u to the alpha minus 1 over, here you're going to have, see, then u to the beta go to the top, okay, u to the beta go to the top, see this guy, this one give you u, see. Then we can, and comma, u is less than 1, see, u is less than 1, u is less than 1. Very interesting. F of u 1 over beta alpha comma beta, then you're going to have this one u to the power of beta minus 1. I'm going to bring this 1 to the top, it becomes minus, I will combine it, this one times 1 minus u to the alpha minus 1 and u being less than 1. U being less than 1 means u should be between 0 and 1. See, that's the same thing. Look at this one. If you go ahead and look at this structure, you are very familiar with this structure. This is the equation, equation of the density of beta function of first kind. You see? You have the second kind, and with the certain kind of adjustment or transformation, you can come up with the beta function of first kind. Look at what I'm going to do. I'm going to write this one, 1 over beta, beta times alpha, beta comma alpha. I'm going to flip this one, and I'm going to write this way, see, beta minus 1 times 1 minus u alpha minus 1, u being between u 0 and 1, see. So this is nothing but, you see, I wrote pretty much same thing, but I flipped this one. Doesn't matter whether you're going to write beta function as a beta comma alpha or alpha comma beta, because this is nothing but gamma beta gamma alpha over gamma alpha plus beta. See? So once you calculate either this way or this is equivalent to, see here it's like what? Gamma alpha, gamma beta, gamma alpha plus beta. So these two are equivalent. In that way, it doesn't matter whether you're going to write beta function alpha comma beta or beta comma alpha. This is beta, this is alpha, this is beta function. So once you have this structure, this is nothing but you can very clearly say that U is U, capital U, is distributed. See, the single tilde means, this is a single tilde. Single tilde means is distributed as what? Beta. This is for the beta distribution. This is for beta distribution with shape parameters beta and alpha. See? Beta and alpha. So you're going to end up with another beta of, therefore U has a density of beta distribution of the first kind. Thank you very much. We'll see you later. Bye-bye.